Somewhere over the open Atlantic, 2,000 miles from the nearest coastline, two storms are spinning at the same time. Not side by side, ignoring each other. Spinning around a shared center point like two ice skaters who've grabbed hands and started a turn. That's not a metaphor I'm exaggerating for effect. That is, physically, what happens when two rotating storms get close enough to feel each other's pull. Here's a way to picture the scale of what we're talking about. A single hurricane can be as wide as the entire state of Texas. Now picture two Texas-sized spinning wheels, both a few hundred miles apart, both pulling on the same pocket of ocean air. That's the setup. That's the thing meteorologists watch for, and honestly, kind of dread. And I called this video "Two Dangerous Storms Are Coming," and I know that sounds like a headline built to scare you into clicking. But that's not quite the full picture. What I actually want to walk you through is a real, well-documented weather pattern. One that has happened before, will happen again, and is more interesting and more useful to understand than any single scary headline could ever be. By the end of this video, you're going to understand three things. First, why storms sometimes team up, either by literally spinning around each other or by lining up one after another like cars in a traffic jam. Second, how scientists actually figured this out. And it starts with a man, a bathtub, and a very strange question. Third, what this pattern means for you if you live anywhere near a coastline or anywhere weather systems tend to stack up, and what you can actually do about it that isn't panic. I'm going to be upfront with you. The first half of this video is the uncomfortable part. I'm going to walk you through exactly how bad these compound storm events can get, using real history, real numbers. I'm doing that on purpose before I get to the good news and the practical stuff, because I'd rather you sit with the real risk for a few minutes than have me sand off the edges to keep you comfortable. Stick with me through the hard part. The second half is where this gets genuinely useful. Okay, let's start with the traffic jam, because it's actually the easier of the two patterns to picture, and it's the one that causes more damage worldwide than the dramatic spinning storm scenario. Think about the sky above you right now as a highway. Weather systems, storms, fronts, waves of moisture are constantly moving. Along that highway, usually west to east in the middle latitudes, pushed along by the jet stream, which is basically a fast-moving river of air 5 or 6 miles up. Under normal conditions, that highway keeps moving. One storm rolls through your town, dumps its rain, and keeps driving east toward the next town. Traffic flows. But sometimes, a big, slow-moving zone of high pressure parks itself in the middle of that highway. Meteorologists call this a blocking pattern, and the name is exactly right. It's a stalled truck in the fast lane. And when that happens, every storm behind it has nowhere to go. They don't disappear, they just queue up. One after another, they get funneled into the same narrow lane, and they all dump their rain, or their wind, or their surge onto the exact same stretch of ground over and over, days apart, sometimes only hours apart. This is sometimes called storm training, and it's a good name for it too, because it looks exactly like a train. One engine, and then car after car, running along the same track. Each individual storm might not sound that dangerous on its own, but when the ground has already taken on all the water it can hold, storm number 3 doesn't have anywhere to go. It just sits on top of storm number 1 and storm number 2, and that's when a normal storm season turns into a flood catastrophe. You've almost certainly heard the term atmospheric river before, and it's actually the clearest real-world example of this exact traffic jam pattern. An atmospheric river is a long, narrow band of concentrated water vapor moving through the sky, sometimes stretching over 1,000 miles, carrying more water in vapor form than the mouth of the largest rivers on the planet carry as liquid. On its own, one atmospheric river making landfall is just a strong rainstorm, often a beneficial one, since a lot of the world's mountain snowpack and reservoir supply depends on exactly this kind of moisture arriving each year. The problem starts when the highway gets blocked, and instead of one atmospheric river passing through and moving on, 3 or 4 of them line up and strike the same stretch of coastline within the same 2 or 3 weeks. California experienced almost exactly this sequence over the winter of 2022 into 2023, with a series of these systems arriving back-to-back over about 3 weeks. No single one of those storms, on its own, would have been considered historic. It was the queue, the sheer number of them, arriving faster than the ground. The rivers and the reservoirs could recover between hits. That turned an ordinary wet season into widespread flooding, levee failures, and mudslides across parts of the state. That's storm training in its most literal, most documented form. Not one dramatic monster storm, but an ordinary, explainable weather pattern repeating itself just a little too many times, a little too close together. Before we leave the traffic jam pattern, there's one more piece worth understanding, because it explains why some ocean basins see this far more often than others. Fuel. A storm, at its core, is a heat engine. It pulls energy from warm ocean water the same way a car pulls energy from gasoline. Warm water evaporates faster, the water vapor rises and condenses into clouds, and that condensation releases heat, which powers the storm's winds. Cooler water simply can't feed that engine the same way. So when a blocking pattern sets up over a stretch of ocean that's running unusually warm, every storm funneled down, that same lane arrives with a full tank, one after another, instead of gradually weakening the way storms often do once they've used up the warmest patch of water beneath them. This is part of why the exact same traffic jam pattern can produce a mild, unremarkable string of storms in one year and a genuinely historic sequence in another. The highway is identical, but the fuel sitting underneath it is not. Let's talk about the other pattern now, the one from the top of the video. Two storms literally spinning around each other. This is called the Fujiwara effect, and it's rarer and honestly stranger than the traffic jam pattern. Here's the plain version. Any spinning storm, a hurricane, a typhoon, even a smaller low-pressure system, creates a kind of invisible whirlpool in the air around it. Under normal conditions, that whirlpool is alone, and it just spins in place, drifting with the larger wind patterns around it. But if a second spinning storm gets close enough, usually within about 900 miles for two moderate-sized systems, though the exact number depends on how strong and how wide each storm is, each one starts to feel the other's whirlpool. And instead of drifting independently, they start to orbit a shared point between them, like those ice skaters again, still holding hands, spinning slowly around a center that belongs to neither of them alone. Sometimes that dance ends with the storms just gradually pulling apart again. No harm done, no headline. Sometimes the smaller storm gets pulled directly into the bigger one and absorbed completely, which actually can be a good outcome because it takes one storm off the board. But sometimes, and this is the version we worry about, the two storms get close enough to merge into a single, larger, messier system. One that can pull in even more warm ocean moisture and grow stronger than either storm was on its own. And because they're both changing direction as they spin around each other, their paths become genuinely hard to predict. A storm that was forecast to curve out to sea can suddenly bend back toward land because its dance partner just pulled it off course. Let's slow down on that last point, because it's the part that actually matters most to forecasters, and it's easy to skim past. A normal lone storm moves in a way that's fairly predictable days in advance, because it's mostly being steered by the larger wind patterns around it. Think of it as a single car being carried along by a wide, steady river current. Forecast models are genuinely good at tracking that. But once a second storm enters the picture close enough to start the Fujiwara dance, that steady river current stops being the only force in play. Now, each storm is also tugging on the other one, and that tug changes constantly as the distance between them changes, which changes the tug again, which changes the distance again. It becomes what mathematicians call a feedback loop. The outcome affects the next moment, which affects the outcome after that. That's exactly the kind of situation where small early differences in a forecast model can snowball into big differences in the predicted path, just a few days later. It's not that forecasters are worse at their jobs during these events. It's that the problem itself has genuinely become harder in a way that has nothing to do with human error and everything to do with the physics of two spinning systems influencing each other in real time. This has actually happened before, on the record, more than once. In the fall of 1995, 3 tropical systems were active in the Atlantic basin within the same short stretch of days, and forecasters had to track how each one's presence was subtly bending the expected path of the others. A few years earlier, in the Western Pacific, which sees typhoons interact with each other more often than the Atlantic does, simply because more storms form there each year. Meteorologists have documented multiple cases where 2 typhoons approached each other, began the Fujiwara rotation, and then one of them took a sudden sharp leftward turn that no single storm model would have predicted, on its own. None of these were treated as mysteries by the scientists watching them. They were treated as textbook cases, dramatic but explainable, once you understood that you were no longer looking at one system, but at 2 systems locked in a shared orbit. I want to pause here and do the myth debunking part now, while this is fresh, because I know exactly what shows up in the comments whenever a video talks about 2 storms at once. Some people will say this is a brand new phenomenon, proof that the weather is being deliberately engineered, or that agencies are hiding how common this is. I want to be straightforward with you. None of that is true, and it's not even a new idea. The Fujiwara effect has been documented and studied for over 100 years, in ordinary published science, openly available to anyone. Storm training and blocking patterns are taught in introductory meteorology classes. These aren't secrets. They're not new. They're not artificial. They are simply how a fluid, and the atmosphere is a fluid, just like water, behaves when you put more than one spinning system into it. The reason you're hearing about this more now isn't a conspiracy. It's that satellites and forecast models have gotten dramatically better at spotting these interactions days in advance, which means meteorologists can now warn you about a merging storm system before it happens, instead of just describing it afterward. There's a second, quieter version of this myth worth addressing, too. The idea that any unusual-looking storm behavior on its own is proof that something is being hidden from the public. I understand where that instinct comes from. A storm that suddenly changes direction, or two systems that appear to merge into something bigger on a radar loop, does look strange if you're seeing it without the underlying physics behind it. But strange looking and secret are two very different things. Every major forecasting agency in the world publishes its storm track models, its wind speed estimates, and its reasoning openly in real time, specifically so that independent scientists and even ordinary members of the public can check that reasoning against the data. Meteorology isn't a field known for hiding its work. If anything, it's one of the more transparent, most publicly scrutinized branches of applied science that exists, precisely because so many people's safety depends on getting it right and being checked. I also want to be honest with you about where real uncertainty does exist, because pretending there's none would be its own kind of dishonesty. Scientists don't fully agree, for instance, on exactly how much a warming ocean is shifting the frequency of these compound storm events versus simply making the storms that do occur more intense once they form. Those are two different questions, and separating them cleanly in the data is still active, ongoing research. That kind of open disagreement isn't a weakness in the science. It's what honest science sounds like when it's still working through a genuinely hard question. And it's very different from the kind of manufactured doubt that gets thrown around in comment sections. Now let's do the detective story, because this is honestly one of my favorite pieces of weather history and almost nobody knows it. In the early 1920s, a Japanese meteorologist named Sakuhei Fujiwara wasn't studying hurricanes at all. He was studying something much smaller and much stranger: how two whirlpools of water behave in a shallow tank when you spin them close together. He wasn't trying to predict typhoons. He was just curious about vortices, the general physics of spinning fluid, the same math that describes water going down a drain or smoke curling off a candle. He spun up two little whirlpools in his tank, side by side, and watched what happened. And what he saw surprised him. The two whirlpools didn't just spin in place next to each other. They started to circle around a shared center point between them, exactly like a pair of dancers. Sometimes they'd merge into one bigger whirlpool. Sometimes the smaller one would get flung outward and break apart. He published this observation in 1921, describing the general behavior of paired vortices in a fluid, years before anyone connected it directly to actual typhoons out over the Pacific. It took other meteorologists, watching real storm tracks over the following decades, to make the connection. Hurricanes and typhoons are, among other things, enormous vortices in a fluid, the atmosphere, and Fujiwara's simple tank experiment turned out to describe their behavior almost perfectly. That's the detective story here. A scientist studying something as small and unglamorous as water in a tank ended up handing meteorologists, a century later, the exact tool they needed to explain why some of the most dangerous storm tracks in history suddenly curved in ways nobody expected. Here's the part of the story that I think gets skipped the most, and it's the part that actually makes it a detective story instead of just a fun fact. For years after Fujiwara published his work, forecasters watching real storms out over the Pacific kept running into paths that just didn't make sense under the old assumption that a storm moves however the surrounding wind tells it to move. A typhoon would be tracking steadily northwest for days, behaving exactly the way the models expected. And then, with no obvious change in the surrounding weather, it would suddenly hook sharply to the left, as if something had reached out and physically redirected it for a while. These hooks were treated as forecasting failures or blamed on bad data. It wasn't until someone went back and checked whether a second, smaller storm had been sitting nearby the whole time, often one too weak to make headlines on its own, that the pattern clicked into place. The failure wasn't a failure at all. It was Fujiwara's tank experiment, playing out at full scale, thousands of feet in the air, exactly as a man studying spinning water had described it decades earlier. That's the reveal. The mystery wasn't in the storm. It was in what the forecasters weren't yet looking for. It's worth understanding how forecasters actually